Welcome to Q&A Wire.
In this question, we have a rocket being propelled upward by its engines. I'm going to draw it as a dot just to make life a little bit easier. So it takes off from rest, and it has an upward acceleration given by 3.2 meters per second squared. And when it reaches a level of, I'm going to call it delta Y from the ground, of 950 meters, the fuel runs out, but the rocket is going to continue upward with some, I'm going to call it V1 here, and then under the influence of gravity, the rocket is going to slow down to a stop at the top, where it will have a velocity at 0.2 equal to 0 meters per second, and then I'm going to sketch it just as a dashed line off to the side. The rocket is then just going to fall back down to the Earth. And we are going to find what's the velocity when it runs out of fuel, how long does it take to reach 950 meters, what's the maximum altitude, and how much time total does it take to reach maximum altitude, what velocity does it strike the Earth, and how long total is it in the air. Woo! So let's start with that velocity when it runs out of fuel. So that's what I called V1. Well, we want V1. We have a V naught that is 0 meters per second at the ground. We have an acceleration equal to positive 3.2 meters per second squared, and we have a vertical displacement of 950 meters. There's nothing about time in here, so this is a great candidate for V squared equals V naught squared plus 2a delta y. And so we can say that V1 will be the square root of V naught squared plus 2a delta y. So the square root of 0 squared plus 2 times 3.2 times 950. And I get a velocity when the rocket runs out of fuel of 77.97 meters per second. You might call it 78 if you're keeping to two significant figures, because the given values are all reported to 2 sig figs. And now, how long to reach this point? So we have a couple of ways to go about this. In the event you had trouble with finding that velocity, so we want t to get there. In the event you had trouble finding that velocity at the end of this acceleration period, we can use an equation that doesn't need that velocity. And it's going to be delta y equals v naught t plus 1/2 a t squared. So 950 equals 0 plus 1/2 times 3.2 times t squared. And so t is going to end up being the square root of 950 divided by 1.6, because I did a half of 3.2. Divide both sides by 1.6, and then take the square root, and that gives me a time of 24.37 seconds, which, becomes 24 seconds if you're reporting two significant figures. I do want to point out that you could also have done V1 equals V naught plus AT if you had success finding that velocity, but I'm not going to show you that. So to reach the maximum altitude, so we are going to need to So we are going to need to find what I called a height delta H above the point where the rocket ran out of fuel. And then H max is going to be the entire distance from the ground, where H max will be equal to the delta H that we are about to find, plus the original 950 meters. And how are we going to find delta H? Well, I think it's easiest to note that V2 is 0 meters per second when it reaches that maximum height. We have a V1 equals 77.97 meters per second, and we have an acceleration equal to that of gravity, negative 9.8 meters per second squared, and we are being asked to find delta H. Seems like a great candidate for that same equation we used back in part A. So V2 squared equals V1 squared plus 2a delta H. 0 squared equals 77.97 squared plus 2 times negative 8 times delta H. And so delta H is going to be the opposite of 77.97 squared. I didn't calculate it before I rearranged my equation. I just plugged everything in the way you're seeing me write it now. And that gave me 310 meters. And so I can now say that H max is going to be 310 meters plus 950 meters, which gives me 1,260 meters. And how much time total does it take to reach that altitude? Well, we can find the time to get from V1 to V2 and then add that to the time to reach 950 meters. So, let me grab another color. How about pink? That'll be fun. So, the time here, we'll call it time 2. No, we won't call it time 2. We'll just call it time t. Is going to be the time to reach what I'm calling point 2, the top, plus the time to reach point 1, which is 950 meters. So we clearly need to find that time to reach the maximum height. And like I said, I noticed that we could do V2 equals V1 plus AT. So 0 equals 77.97 minus 9.8 times t. And I get a time of 77.97 divided by 9.8, which gives me 7.96 seconds. And so I can take my 7.96 plus my 24.37, and I can get a time of 32.33 seconds. And now, with what velocity does it strike the Earth? Well, I am again looking at, we could call it V3 upon landing. I didn't mark that in my diagram, but V3 will be equal to V2 squared plus 2A times the change in height from H max. So we're really going to make it, I really could just call it negative H max. I have to call it negative because it's going to displace downward. So V3, when we land on the ground, is going to be equal to 0 squared plus 2 times negative 9.8 times negative 1,260 meters. And that gives me 157 meters per second. And then how long total is it in the air? We could go ahead and find the time from that maximum point and add it to our total time to reach H max. So in fact, let's do that. So I'm going to call it T total equals T3, which is the time to reach the ground, plus T. And we have a number of ways we could do this. You could do delta Y equals V naught T plus a half AT squared. Or you could do V3 equals V2 plus AT, whichever strikes your fancy. I think I'm going to do 157 meters per second downward equals 0 minus 9.8 T. And that gives me a T equal to 157 divided by 9.8, which is 16.02 seconds. Man, we are just going to call that 16 seconds. And so now we can say that T total is going to be this extra 16 seconds plus the 32.33 seconds that we had to reach the top. And that gives me 48.33 seconds. If you wanted to use the delta Y equation, you would again make this equal to minus H max and then V naught. This is going to be V2 up there at the top in order to find that time to get from the top down to the ground to add on to the time it took to get to the top.